thermal step to calculate the entropy along those steps. So entropy is a state function. You can calculate the changes along any path, so find reversible paths, calculate entropy along those paths. I could also ask you a question about the heating of a substance, and maybe we take that substance through phase changes, right? As we dump heat into the system, entropy is increasing, so you got the heating capacity, the Cp over T dt, and you integrate that from the initial temperature to the final temperature, and that's your entropy change. For the phase change, remember entropy is dq reversible over T. For the phase change, dq reversible is going to be delta H of the process. Right? So if I tell you you got something that goes through a phase change and you need to figure out the entropy, you're going to need to look at that question and say, okay, where did he tell me delta H? Because delta H is going to be my Q, and you're going to take that over T, right? So you got that. There's going to be an entropy problem. I'm going to ask you about the things that contribute to entropy. Entropy increases with the volume of the system. The volume of the system increases, you've got more states that are accessible to the system, so you've got more disorder. Entropy increases when you stick energy into a system. You stick energy into a system, you've got more energy packets to spread amongst the states available to the molecule. And so you need to know that entropy increases with energy, it increases with volume. I'm going to ask you something about that. Let's get away from entropy for a second, and let's go to the Gibbs free energy. So the Gibbs free energy, delta G equals delta H minus T delta S. Now, we had a total differential for G. We said dG was equal to VdP minus S dt. I could ask you about, I could ask you a question about how, exam 1, we've got the enthalpy question. And I say delta H naught at some temperature is such and such a value. And then I ask you what's delta H at some other temperature. For that, you needed to know that dH was Cp dt, right? And you had to say that delta H at T2 was equal to H naught of the products plus the integral of C sub P dt minus H naught of the reactants minus C sub P of the reactants dt. Right? The same thing can be done with this equation. If I give you a G naught, and I say, this is your G naught at some particular pressure or temperature, what's G going to be at some new pressure or temperature? Then you would have to go to this equation. And you'd have to say, delta G at T or P2 is equal to G naught of the products minus the integral of, say it's a pressure thing, or plus the integral of V of the products dP, right? And delta G is that minus G of the reactants plus the integral of VdP. Or I could give you the entropies or something like that. So we already know that we have to correct things for non-standard states, right? I could use this equation. Or I could do it like we did with the water problem that we did in class, where we said water goes spontaneously to ice under certain conditions and non-spontaneously at others. Figure out how that thing changes with non-standard temperatures. And for that one, you had to take into account the changes in delta H and delta S with temperature. Do you remember that problem? So we all did that together. So I could cast it that way. I could say, figure out what delta G is at some non-standard temperature by accounting for changes in delta H and delta S, or I could say, figure out what delta G is at some non-standard pressure or temperature by accounting for VdP or SdT. Two different ways I can go about that. I promise you I will go about that one of those ways. So be prepared to run that kind of a calculation. I'll get kicked out of here by the next guy pretty soon here. All of the stuff that we did on, you've got the lecture video, especially the stuff on the two component systems, go back to those phase diagrams and make sure that you understand those. You had minimum boiling azeotropes, you had the maximum boiling azeotropes for the two component systems. And we said that these were a function of the strengths of the AA, BB, AB interactions. Know which one of these diagrams corresponds to stronger AB interactions than AA interactions, and know which one of those diagrams corresponds to weaker AA or AB interactions, etc. It all has to do with, if you go back and watch the video that we recorded, it all has to do with the strengths that those molecules are holding on to each other with in the solution. So the stronger they're being held to the solution, the harder it's going to be to get those guys to go out. Here's an important one. Obviously know the single component phase diagrams. I think you guys are pretty good on those. But go back and rewatch the lecture where we talked about the chemical potentials of the different phases for the single component system. So we had a bunch of lines that we drew together that had different slopes. I forget what the hell the slopes were. They were something. Anyway, they had different slopes, and the points of intersection were the points of equilibrium, right? And we said that changes in pressure and temperature affected the points of equilibrium. These accounted for freezing point depressions, boiling point elevations. Go back and look at that lecture and make sure that you know what those diagrams mean and how we got to derive the freezing point depression, boiling point elevations, etc. Osmotic pressure. Every single professor that's ever taught thermodynamics has had an osmotic pressure question on an exam, and I will too. So there's one in the homework. If you don't know how to solve that one, send me an email or something like that. Whatever, we'll talk about it. But you need to be prepared to solve an osmotic pressure calculation. And then for the single component systems, we said that there were specific equations that related the equilibrium conditions along the solid gas boundary and the liquid gas boundary. And that guy looked like natural log of P2 over P1 was equal to delta H of the transition over R times 1 over T final minus 1 over T initial. Know how to use that equation. I will ask you to use that equation. All right, so I got to get out of here before the next class comes in. I'm here as long as you need me today, but if I haven't heard from you by 3 o'clock, I'm going home. So, what's that? Oh yeah, homework is right here. Creative homework.